In this lesson, we will talk briefly about limacons and cardioids. Taking its name from the Latin word limax, or snail, these curves often take the shape of a snail shell. The equations for these curves take the form of either one of the following, where a and b are non-zero real numbers. We have r equals a plus or minus b times sine of theta, or r equals a plus or minus b times cosine of theta. Now, the general shape of these curves are dependent on the values of a and b. In this section, there are a couple limacons that are demonstrated, and you can use those for reference. However, as you start to see more of these curves, some of the patterns with a and b will present themselves. If you were to compare the constant term a to the coefficient on your trig function b, and if that value of a is less than b, what you will have is a limacon with an inner, what we could call loop, meaning that you will have a limacon that, for example, takes a shape such as this, where we have the curve that comes inward, intersects through the origin to create, or the pole, to create an inside loop. This is what will happen if your constant term is less than the coefficient on your trig function. If the value of a, the constant term, is equal to the coefficient on your trig function, you will have a special kind of limacon known as a cardioid. A cardioid is named as such as the shape of this graph looks very similar to a heart, which is demonstrated with the second example on the right side here. This example looks kind of like a heart, in this case turned on its side. These kind of limacons hit the pole, they intersect at the pole, but they do not go through it to create that inside loop. And lastly, if the value of your constant term a is larger than the coefficient term b, then you will have what is called a convex limacon. That means that you have a curve that does not intersect through the origin and mostly just kind of flattens out on one side. I normally describe this similar to a deflated basketball or something like that. There are other patterns that you can see with limacons and cardioids. For example, whatever trig function you have, you can think about will define the major axis of the limacon or cardioid. For example, all three of these graphs shown on the side as examples, these are all ones that are going towards what we would call on the Cartesian plane, they're going towards the positive x-axis. They seem to be stretching further along the x-axis than they do along the y-axis. This is because all of these graphs are ones that are made based on an equation involving cosine, which, on the Cartesian plane and in the unit circle, we tend to associate with the x-coordinates. If you are working with equations involving sine instead, then you're going to have these kinds of graphs, but they're going to be more vertically oriented. There are other patterns as well that you may find when looking at how a and b combine or add or subtract that can help define values such as the radius of this inside loop. But I will leave that for you to explore.